All right, so ready to dive into some quantum stuff? Today's focus, the quantum approximate optimization algorithm. Catchy, right? We usually just call it QAOA.
Yeah, much easier.
So to guide us through this, we've got Jörg O. Schneppat's essay. It's called QAOA, effiziente Lösungen durch Quantenoptimierung.
Quite a mouthful. But yeah, it really gets to the heart of what makes this algorithm so interesting, especially now with, all the buzz around quantum computing.
For sure. Now, for our listeners, and I know a lot of you are really into this stuff, think of this deep dive as like your express lane to understanding QAOA. No need for detours into the super technical weeds.
Yeah, we're going for the big picture here.
So what's the deal with QAOA? It's all about finding good solutions. Not necessarily perfect, but good enough for those really tricky problems. You know, the kind that even our best computers struggle with. Like, imagine you're trying to plan the absolute most efficient delivery route for like 100 different stops.
Or think about managing a huge investment portfolio where you're trying to balance risk and reward.
Tons of possibilities, and figuring out the absolute best one, well, that can take a ridiculous amount of computing power.
And time. Lots and lots of time.
So that's where quantum computing, and specifically QAOA, comes in. It's a clever blend of quantum mechanics and good old-fashioned classical computing. We're talking about harnessing the strangeness of the quantum world to explore solutions in a way that's just impossible for regular computers.
Yeah, it's kind of like instead of checking each possibility one by one, quantum computing lets you look at them all at the same time. Superposition, they call it.
We'll get to that. But first, Schneppat sets the stage by taking us back to the roots of quantum computing. The 1980s, big hair, synth music, and the very first whispers of a new kind of computing.
It all started with folks like Richard Feynman and David Deutsch. Feynman, brilliant guy, realized that traditional computers would hit a wall when it came to simulating quantum systems. I mean, think about it, trying to track the behavior of every single electron in a molecule. That's a mind-boggling number of calculations.
It's like trying to write a novel on a sticky note, just not enough space.
Exactly. And Deutsch, he came up with this idea of a universal quantum computer, a machine that could theoretically tackle any computation a classical computer could, but with the potential to blow it out of the water for certain kinds of problems.
So these were the seeds being planted, the early visionaries. But when did things really start to click? Schneppat mentions Peter Shor's algorithm in 1994. That seemed to be a turning point.
Yeah, Shor's algorithm was a real game changer. It showed that a quantum computer could factor huge numbers way, way faster than any known classical algorithm.
And that's a big deal, right? Because factoring large numbers is at the heart of a lot of our encryption methods, the kind that keeps our online transactions secure.
Exactly. Shor's algorithm was this wake-up call. Hey, quantum computing isn't just theoretical. It has the potential to disrupt some pretty fundamental stuff. And since then, well, as Schneppat lays out, the field has exploded.
Yeah, I mean, we've got companies like IBM and Google building quantum computers based on superconducting qubits. Then you have companies like IonQ using trapped ions. And there's a whole new wave of programming languages like Qiskit and Cirq springing up.
It's an exciting time to be watching this field, that's for sure.
Definitely. But all this effort, all this investment, where's it leading? Schneppat emphasizes the importance of what are called optimization problems. And this is where QAOA really shines.
Totally. Think about it. Optimization is everywhere. Logistics companies obsessing over the most efficient delivery routes. Financial analysts trying to build the perfect portfolio. Energy grids needing to balance supply and demand in real time. Even biologists trying to understand how proteins fold into these incredibly complex shapes.
These are real-world headaches, not just some academic brain teaser.
Exactly. And many of them fall into a category called NP-hard. It basically means the harder the problem gets, the more variables, the more possibilities, the longer it takes a classical computer to find the very best solution. We're talking exponentially longer.
So for super complex problems, classical computers just run out of steam.
Pretty much. And that's where QAOA steps in. Schneppat tells us that it was proposed in 2014 by Edward Farhi and his team. Their goal was to create a quantum algorithm that could be used on the kind of quantum hardware we have right now, which, isn't perfect, it's noisy, it's limited, but it's a start.
So a practical approach designed for the here and now.
Exactly. And here's the cool part. QAOA is this hybrid. It blends the power of quantum computation with the finesse of classical algorithms.
A quantum classical tag team.
Exactly. And it's especially good at tackling problems that can be expressed as a mathematical function. Think of it like this. You take your problem, whether it's maximizing profits or minimizing travel time, and you translate it into a mathematical equation. That equation is your objective function, the thing you want to optimize.
So the quantum computer takes this equation and crunches the numbers in some crazy quantum way?
Kind of. But it's not just brute force. QAOA is about using the weirdness of quantum mechanics to explore the landscape of all possible solutions simultaneously. It's like being able to flip a million coins at once and see all the possible combinations.
The power of superposition.
You got it. And then on the classical side, we have algorithms that are constantly tweaking and adjusting the parameters that control the quantum computation, guiding it towards better and better solutions.
It's like a dance between the quantum and the classical. One explores, the other refines.
A beautiful analogy. And Schneeppert really emphasizes why this hybrid approach is so perfect for our current situation in quantum computing. We're in what's called the NISQ era.
NISQ, like a quirky new music genre.
Not quite. It stands for Noisy Intermediate Scale Quantum. It basically describes where we are right now with quantum computers. They're powerful, yes, but they're also quite limited and prone to errors.
Yeah.
We don't have those super stable, error-corrected machines we see in sci-fi just yet.
So we have to work with what we've got.
And QAOA is perfectly suited for that. By combining quantum exploration with classical fine-tuning, it avoids the need for those long, complex quantum computations that would just get bogged down by errors on current hardware.
So it's a way to get meaningful results now rather than waiting for some perfect quantum future.
Right. And that's a big part of why QAOA is such a hot topic. It's about getting practical value from quantum computers today.
So QAOA, it's this hybrid near-term solution to tough optimization problems. But to really get it, we need to delve into the quantum mechanics a bit, right? Schneeppert breaks down those core principles that make QAOA tick.
Yeah, we've got to talk about superposition, entanglement, and measurement. These are the pillars of quantum weirdness.
All right, superposition first. This is the whole a qubit can be a 0 and a 1 at the same time thing, right? Still blows my mind.
Yeah, it defies our everyday logic. But in the quantum world, things can exist in multiple states at once. The qubit, it's not just a 0 or a 1. It's a blend. A combination of both, with a certain probability of being either when we measure it. Schneeppert explains this using those Greek letters alpha and beta, but the main takeaway is that this both-at-once ability allows quantum computers to explore way more possibilities than classical computers.
It's like running multiple calculations in parallel, all at the same time.
That's a good way to think about it. Then there's entanglement, which Schneeppert describes as this spooky connection between qubits. You could have two qubits, even separated by a large distance, and their fates are intertwined. Measure one, and you instantly know something about the other.
Einstein called it spooky action at a distance, right?
He did. And entanglement is a powerful resource in quantum computing. It allows us to create these complex, correlated states that are impossible in the classical world.
So we've got superposition, multiple states at once. We've got entanglement, spooky connections. What about measurement? How do we get an answer out of this quantum fuzziness?
Measurement is the bridge between the quantum and the classical, as Schneeppert puts it. When we measure a qubit, we force it to choose. It collapses from this blurry superposition into a definite 0 or a 1. The probability of each outcome depends on those initial probabilities, the alpha and beta values that define the superposition. And Schneeppert also dives into the different ways we can physically realize these qubits, superconducting circuits, trapped ions, even photons. Each technology has its own pros and cons.
So we're really talking about controlling the microscopic world to do our computational bidding. It's incredible. But let's go back to the algorithm itself. Schneeppert places QAOA within a family called variational quantum algorithms, or VQAs. What are these, and what makes QAOA special?
VQAs are like the all-star team of near-term quantum algorithms, and QAOA is definitely a star player. As Schneeppert explains, VQAs are all about combining parameterized quantum circuits with classical optimization routines. Think of it like a feedback loop.
Okay, walk me through that.
So you have a quantum circuit, which is basically a sequence of quantum operations. Some of these operations are controlled by parameters, like little knobs you can tweak. You run this circuit on a quantum computer, get some results, and then feed those results into a classical algorithm.
And the classical algorithm is like the coach, making adjustments based on the team's performance.
Exactly. It analyzes the results and says, okay, let's tweak this parameter, adjust that one, trying to find the settings that give the best possible outcome. And the goal is usually to minimize something called a cost function.
The cost function, it's like a measure of how bad our solution is, right?
Got it. Lower cost means a better solution.
Mm-hmm.
And QAOA is a specific type of VQA that uses a very particular kind of quantum circuit, one that's built up of alternating cost and mixing Hamiltonians.
Hamiltonian.
Yeah, they're these mathematical objects that essentially describe the energy of a quantum system. The cost Hamiltonian encodes the problem we're trying to solve, and the mixing Hamiltonian helps the algorithm explore different solutions. And they're controlled by those adjustable parameters, gamma and beta.
So the classical algorithm is tweaking gamma and beta, trying to find the sweet spot that minimizes the cost function. It's like fine-tuning a radio to get the best signal.
A perfect analogy. And Schneppert points out that QAOA's relative simplicity and flexibility make it a great starting point for working with VQAs on those noisy, error-prone quantum computers we have today. It's kind of like the hello world of VQAs.
Simple yet powerful. I like it. Now, Schneppert digs into the core idea behind QAOA, and it has to do with finding the lowest energy state of a quantum system. How does that translate into solving our optimization problems?
It's all about the analogy between energy in a quantum system and the cost of a solution to our problem. Schneppert walks us through the two main steps in QAOA. First, we start with a simple quantum state, often a superposition where all possible solutions are equally likely. Then we apply those cost and mixing Hamiltonians repeatedly. Think of it like gently nudging the system towards lower and lower energy states.
So we're sculpting the energy landscape of the quantum system.
Precisely. And the specific way we apply those Hamiltonians, the duration and order, that's all controlled by those gamma and beta parameters.
So we're essentially choreographing a quantum dance guided by those parameters.
I love that. It's a beautiful way to think about it. And the ultimate goal is to find the values of gamma and beta that lead to the lowest possible energy state, because that state will represent the solution to our optimization problem with the lowest cost.
Quantum energy minimization equals real-world problem solution.
Nailed it.
To make this more concrete, Schneppert uses the max cut problem as an example. Can you walk us through that? I always like graph problems.
Me too. So the max cut problem is all about dividing a network into two groups, so that you have the maximum number of connections crossing between the groups. Think of it like splitting a social network into two rival factions, and you want to maximize the number of friendships that cross the divide.
Sounds messy.
It can be.
Yeah.
But mathematically, it's a classic optimization problem. And Schneppert shows us how to define a cost Hamiltonian for this problem. It basically assigns an energy penalty for each connection that doesn't cross the divide between the two groups.
So lower energy means a better cut, more connections crossing the divide.
Right. And then we have the mixing Hamiltonian, which, as Schneppert explains, helps the algorithm jump around and explore different possible cuts, making sure we don't get stuck in a solution that's just locally good, but not the absolute best.
So it's like the mixing Hamiltonian is shaking things up, preventing the algorithm from getting too comfortable.
Exactly. And Schneppert provides a formula for how the quantum state evolves as we apply these Hamiltonians over and over. Each application is like another step in the dance, guided by those gamma and beta parameters.
Schneppert mentions this parameter, P, the level depth. What's that all about?
The level depth. It's a crucial part of QAOA. P tells us how many times we repeat that dance, that sequence of applying the cost and mixing Hamiltonians.
So more repetitions, better solution.
In theory, yes. A higher P means we're exploring the solution space more thoroughly, which should lead to a more accurate result. But, and this is a big but, more repetitions also mean longer computation times, and that's a problem with our current noisy quantum computers.
Right, those errors start to creep in.
Exactly. So as Schneppert points out, there's a trade-off. We want a high enough P to get a good solution, but not so high that our computation gets derailed by noise. Finding that sweet spot is a big part of the art of using QAOA in the NISQ era.
So it's about finding the right balance for the specific problem and the hardware you have.
Yep.
All right, let's zoom in on the actual implementation of QAOA. Schneppert gives us a step-by-step breakdown. Where do we begin?
We start by preparing our quantum system in a very specific initial state, usually a superposition where all possible solutions are equally likely. It's like setting the stage for the quantum dance. Schneppert provides the mathematical notation for this state, but the main idea is that we're creating a quantum version of a blank slate.
A quantum canvas, ready for the algorithm to work its magic.
Like that. Then we need to define those cost and mixing Hamiltonians that are specific to our problem. Schneppert gives the example of the max cut Hamiltonian again. These are the mathematical instructions that will guide our quantum computation.
The choreography for the quantum dance.
Yep. And then the real fun begins. We apply the cost Hamiltonian, then the mixing Hamiltonian, and we repeat the sequence P times as determined by our chosen level depth. Each application is controlled by those gamma and beta parameters, which are constantly being adjusted by our classical optimization algorithm.
So the quantum computer is doing its quantum thing, exploring solutions, and the classical algorithm is watching the results and tweaking the parameters to steer things in the right direction.
Precisely. And after p iterations, we end up with our final quantum state. This state encodes the information about our potential solution. But to get an actual answer, we need to measure the qubits. And since we're dealing with probabilities, we need to repeat this measurement many times to get a good estimate of the solution.
So measure, measure, measure. Gather that data.
And that data, that's what feeds back into our classical optimization algorithm, telling it how well our current parameters are performing. The algorithm then uses this feedback to adjust gamma and beta, and the whole process starts again.
It's a constant loop of quantum exploration and classical refinement, a true partnership.
Exactly. Schneppat really emphasizes this back and forth, the crucial role that classical optimization plays in making QAA work. He even dives into different classical optimization techniques. Some that use gradient information, some that don't.
So there's a whole toolbox of classical techniques to choose from, each with its own strengths and weaknesses.
Right. It's all about finding the best classical dance partner for our quantum dance. And of course, to do any of this, we need actual quantum computers, and Schneppat gives us a tour of some of the platforms out there.
We've got IBM offering access to their superconducting qubit machines through the IBM Quantum Experience. Google's been making waves with their Sycamore processor. Rigetti Computing's focusing on hybrid systems. And IonQ is all about trapped ions. It's a real melting pot of quantum technologies.
It's amazing to see how much progress has been made in just a few years.
Yeah.
But Schneppat also reminds us that we're still in the early days.
Right. Those NISQ limitations are still there.
Yeah. Noise, limiting qubit numbers, errors in the quantum gates, errors in the measurements.
Yeah.
These are all challenges that researchers are actively working to overcome.
So QAOA is designed to be robust, but it's still got to dance within these constraints.
Exactly. But the good news, as Schneppat emphasizes, is that even with these limitations, QAOA is already showing promise in a variety of applications.
Let's talk about those. Where's QAOA being put to work, or at least showing potential?
Schneppat highlights some exciting areas. Logistics, for one.
Yeah.
We talked about the traveling salesman problem earlier. Well, QAOA could be used to find better routes, especially as the number of stops grows and the problem becomes too much for classical computers to handle efficiently.
So, more efficient delivery routes, less time stuck in traffic. Sign me up.
And then there's finance. Imagine using QAOA to optimize investment portfolios, taking into account all sorts of complex factors like risk, correlations between assets, market fluctuations.
Quantum-powered investing sounds like something out of a sci-fi movie.
It does, doesn't it? But it could become reality sooner than we think. And then there's materials science. QAOA could help us design new materials with specific properties, or even understand how proteins fold into their complex shapes, which could lead to new drugs and therapies.
So from optimizing delivery routes to designing life-saving drugs, that's quite a range.
Yeah, QAOA's got a bright future.
Yeah.
But Schneppat also gives us a balanced perspective, comparing it to classical algorithms. What are the strengths? What are the weaknesses?
Right, because it's not like QAOA is automatically better than everything else out there.
Exactly. Schneppat points out that for smaller problems, classical algorithms can often do just fine. They might even be faster and more efficient than using a quantum computer. And even for larger problems, there are specialized classical techniques that have been honed over decades and can still be very competitive.
So it's not a quantum takeover just yet.
Not quite. But QAOA has some key advantages. It's inherently parallel, thanks to superposition, so it can explore many possibilities at once, and it's good at escaping those local minima, those solutions that seem good but aren't the absolute best.
So it's a powerful tool in the right context. And Schneppat walks us through some of the research that's been done to validate these claims. He mentions the original 2014 paper that introduced QAOA, as well as more recent studies that have tested it on real quantum computers.
Yeah, those experimental results have been really encouraging, showing that QAOA can actually solve certain types of problems more efficiently than classical algorithms. Schneppat highlights some of those success stories, like using QAOA on IBM's Quantum Experience to solve graph problems.
Proof that the theory works in practice. Now, looking ahead, Schneppat talks about the challenges and future directions for QAOA. What are some of the big hurdles that still need to be cleared?
Well, there's the hardware side of things. We need more qubits, longer coherence times, better error correction. We need those quantum computers to grow up a bit. But there are also challenges on the algorithm side. Schneppat mentions this extension called the Quantum Alternating Operator Ansatz, or QAO, which is designed to handle even more complex problems.
So expanding the toolkit, making QAOA more versatile.
Exactly. And there's a lot of research going on in that area. Plus, Schneppat highlights the potential for combining QAOA with other algorithms, both quantum and classical. It's like building a quantum computational symphony, where each instrument has its own unique role to play.
A quantum orchestra. I like it. What about totally new applications? Where might we see QAOA being used in the future?
Schneppat throws out some interesting ideas. Smart cities, using QAOA to optimize traffic flow or energy distribution. Biomedicine, using it to design new drugs or personalized therapies. Even quantum communication networks, using QAOA to improve security and efficiency. It seems like the possibilities are endless.
It's mind-blowing to think about how this algorithm, born from the weirdness of quantum mechanics, could impact so many different aspects of our lives.
It really is. And as Schneppat wraps up in his essay, it's clear that QAOA is a game changer. It's bridging the gap between the theoretical promise of quantum computing and the practical realities of today's technology.
So to sum it all up, QAOA is this powerful hybrid algorithm that leverages quantum mechanics to tackle those really tough optimization problems. It's not a silver bullet, but it has the potential to revolutionize a whole range of fields, from logistics to finance to medicine and beyond.
And it's just the beginning. As quantum computers continue to improve, QAOA and other quantum algorithms will become even more powerful and versatile.
It's an exciting time to be following this field. And to our listeners, keep those questions coming. We're always here to dive deeper into the fascinating world of quantum computing.
Absolutely. There's so much more to explore.
Well, that wraps up our deep dive into the quantum approximate optimization algorithm, inspired by Jorgo Schneppat's insightful essay. Thanks for joining us on this quantum journey. Until next time.